Hello, thank you for attending this webinar organized by the EETS Chair of Artificial Intelligence and Language Technology. EETS, as probably many of you know, means word in Basque, and EETS Center is the Basque Center for Language Technology, part of the University of the Basque Country. This is the sixth of the monthly webinar series of this academic year, and I take this opportunity to recommend you the remaining webinars. You can see the program on your screens right now. Okay, today we have José Andrés González-López with us. It's a pleasure to introduce him to you. He is Associate Professor in the Department of Signal Theory, Telematics and Communications of the University of Granada. And he is a leading research at the intersection of artificial intelligence, computational neuroscience, and speech technology. Previously, he held positions at the University of Sheffield as research associate and also at the University of Malaga as assistant professor. José Andrés González holds a PhD in computer science, and his main research area is the biosignal to speech technologies, spanning both neural signal decoding and also he has done early works on electromyographic signal processing for speech synthesis. His current research focuses on advanced brain-computer interfaces, silent speech interfaces, and clinical application of the speech technology. His lab's works includes projects like Neurolengua, which investigates in the neural substrates of language and speech neuroprosthetics through invasive ECoG, and he has also been collaborating with us, with EETS Center, with our lab, on biosignal to speech conversion projects like Resynth, Restore, and currently in the recently launched Brain to Lang. José Andrés has published over 100 papers in international journals and conferences, and his contributions have earned multiple awards, including recognition for best papers in conferences like AVIOS, ECoG, and Biosignals. So, join me in welcoming José Andrés González to this webinar, and when you want, José Andrés, the floor is yours. You are muted.
Okay, I was saying that thank you very much for the kind introduction. Now? Yes, okay. Okay, thank you. Thank you very much for the nice introduction. First of all, thank you very much for the invitation. It's really a pleasure to be here today speaking to the HITS community. I would like to thank you to you and Aris and Eva for reaching out or organizing this webinar. I really appreciate the opportunity to share my work with a center that is so deeply rooted in language technology. So as you have mentioned, my background is in speech processing and machine learning. For many years, I have worked on different speech technology like automatic speech recognition, speech biometric, and something that we will see later called silent speech interfaces. So these systems, these silent speech interfaces are try to decode speech from without relying into the acoustic signal. For example, using EMG, ultrasound, whatever. So the idea of decoding speech without sound has been part of my research for quite a while. And at some point, through the question naturally evolved. If we can decode speech from, for instance, muscle movement or muscle signal, could we decode it directly from the brain? And that is what this talk is about. So let me start with the problem. As you all know, there are certain neurological diseases that affect speech production. In this slide, I'm showing you an example. I'm sure you all know the case of Professor Stephen Hawking. He suffered from sclerosis, ALS, and this disease rendered him unable to speak in a natural way. So if you remember, he used a device that he controlled with the muscle of his cheese. In addition to ALS, there are other diseases like Parkinson's and stroke that affect speech of the patients, while cognition remains intact. This means that the person knows what they want to say, they can form full sentences internally, but they cannot articulate speech. And often, unfortunately, this loss of speech is permanent. So the core goal of this research is simple but extremely meaningful. Can we restore natural communication to these persons? For some of these patients today, many of these rely on ASC device, alternative augmentative communication device for communication. I'm sure you have seen some of these devices, like these communication boards, or if you remember from Stephen Hawking, he used this kind of eye tracking interface. These systems are very important and they allow these people to communicate again. But of course, they have some limitation. First of all, they are slow, typically 5 to 15 words per minute, while in natural speech, we are talking about 100, 150 words per minute. And also they are very having a high cognitive demanding. So you have to translate linguistic intention into some alternative motor action, so like eye movement, hand movement, etc. They introduce a latency, so the conversation becomes fragmented. So the big question here is, can we bypass this indirect motor pathway and go back to the natural speech plan? And this is where silent speech interfaces I mentioned before come in. So the idea of these silent speech interfaces is really simple. So as we all know, speech does not start with a sound. It starts in the brain with a message. And the acoustic signal is just the final stage of this much longer process that starts in the brain. So instead of decoding this sound wave, silent speech interfaces try to decode other biological signals that are generated by the human body during speech production. This signal can be muscular, like electromyography, or can be neural signal that are the one that I will focus here. And depending of the design of the system, we can translate this neural signal either into text, so actually doing some kind of automatic speech recognition, but using neural signal, or audio. Okay. So now in this talk, I will especially focus on the neural side of these silent speech interfaces. So we will be talking a lot about neural signals. So when we use brain signal, we enter the domain of the realm of brain-computer interfaces. In general, as you may know, brain-computer interfaces are systems that translate brain activity into control signal for controlling external device. You may have seen BCIs for controlling robotic wheelchair, limbs, etc. So in the case of communication, BCIs when they were first applied to communication, most of them work with spelling interfaces. So you can, like when using your mobile phone, they were used for like transcribing information or like typing information letter by letter. In this sense, one of the earliest most established paradigms is what I'm showing here is the P300 speller. As you will see in a minute in a video I'm showing you, this spelling device, in this spelling device, the user look at the grid and shown on the screen, and there are these grid show letters what are randomly flashing, and when the letter the user want to select for typing a word flash, it triggers a signal in the brain that is called a P300. P300 is an evoked potential that is released after 300 milliseconds after the desired letter flashes, and the system can pick up this letter. Let me show you a video to show you how this works. So you can see here, this is the grid where different letters and the letters are randomly flashing. And here you can see on the screen with the different neural signal. And I think that the user is typing vision, and with the desired letter that he wants to use for writing vision flashes, there is like a peak in the signal that around 300 milliseconds that the BCI can pick up to decide that this was the letter. Okay. So what you have seen is just someone just selecting letters one by one using brain activity. There was no speech and no movement. So even though this was a big, remarkable achievement when they were first proposed in the 80s, you can see that these systems are very slow, like typically 10 to 12 words per minute. They require sustain attention and require long training time. So what this system were important time, they are still far from enable natural fluent speech. And this is where next generation BCIs come in. So the idea of this generation BCI that I'm coming here to talk about to you, the idea is doing direct speech decoding from neural signals. So similar to Siri, similar to Alexa, but using high density invasive recordings and modern deep learning architectures. So this is the focus of my talk today. So in particular, in today's talk, I will walk you through this new generation speech BCIs that has been developed over the 10, 15 past years. They are also called neural speech prostheses. So I will show you how the field has evolved in these recent years. And then at the end of the presentation, I will show you some of the research by my group. Okay. So before going into specific papers, I would like to explain to you how I have structured this talk. And I have a structure around what I consider that are the four main components of these next generation BCIs or neural speech prostheses. So the first component is application. So what are we trying to restore with this BCI? Are we decoding text or are we synthesizing speech directly? The second approach, the second component is the experimental paradigm. What does this mean? So what type of task is the participant performing? Is he listening or speech? We are decoding listening, perception, or are he actually producing speech? Is he speaking aloud or imagining speaking? This kind of thing. The third component is the neural recordings, which brain region are being targeted by our speech BCI, which recording modality, and so on. And the fourth and last component is the core of our neural prosthesis, and is the decoding technique and decoding architecture. This includes the signal processing, feature extraction, machine learning models, and so forth. So I will walk you through all these 3 points through this talk. Let me first start with the application. So at the application level, there are essentially 2 main paradigms. So one is brain to text and brain to audio. So in the brain to text conceptually, you can think of it as a type of neural automatic speech recognition. But instead of taking acoustic waveform as an input and mapping to text, we take neural activity and map to text, of course. And the rest of the pipeline, as we will see in some slide, is actually pretty familiar to this audience. So the idea is that we decode neural signal into discrete linguistic units, words, subword, tokens, etc. And we evaluate the performance using standard metrics in automatic speech recognition, such as word rate, word per minute, etc. One of the big advantage of this approach is that we, in theory, we don't need patient recordings, voice recording from the patients. But of course, doing this decoding of tokens introduces some latency, so the communication becomes a little bit more fragmented. The second approach is what I talk, what I mentioned, is the brain to audio. So instead of doing neural automatic speech recognition, we are effectively doing neural to speech synthesis. So we are directly mapping neural activity into acoustic features like spectrogram, vocoder parameter, and generate waveform. So the big advantage of this second approach is that, as we will see for some of the studies, it can enable real-time acoustic feedback. So we can have this user in the loop kind of thing with delays of 10 to 50 milliseconds. But on the other hand, it requires voice recording for the patient or recordings from a voice donor to enable this synthesis. So this was the two main approaches, for decoding neural signal into decoding speech from neural signal. And we will refer to them when we start looking to the different studies in a few slides. So moving on, next thing I will explain is the experimental paradigm. That is something that mainly we technologists, people working in technology, we don't always pay enough attention. But of course, if you talk with somebody from psychology or neuroscience, they will tell you that this is one of the more important things. So experimental paradigm. Okay. So experimental paradigm refers to the type of cognitive task performed by the participant of the neural speech prosthesis, which in turn is the type of task that the speech BCI is able to decode. Okay, so in this diagram, I'm showing you a diagram of one typical task we pass to our participant in our task. So this is a speech production, word production task. What we ask is the participant to either say aloud or imagine speaking a word, in this case, horse. We present this word using three modalities, either as text or audio as an image. Why this is important? Because we will see in a minute they involve different, slightly different brain regions and slightly different cognitive modality. Okay, so because depending on the task engaged in different cognitive processes, this ultimately involve or affect the way the type of information neural feedback will be decoding. So in this slide, I'm summarizing some of the more important key dimensions that we should pay attention when we define our experimental paradigm. I wouldn't want to spend too much time on this, but as you can see, there are like stimulus type. Are we showing the participant written words or pictures? Cognitive modality, is the participant listening to audio, or is he actually producing speech? So we will see that most of the research done on this topic focus on speech production. Production type is the participant reading aloud or imagining speaking, while over speech, like reading aloud, give us a stronger neural signal. Imagining speech is more clinically relevant to participants with speech impediments. Okay, vocabulary side, closed versus open, and language. For language, you can see here, most of the research has been done in English, but there are also some studied with in bilingual settings. Okay, moving on. Next big component of the neural prosthesis is the neural recordings. The neural recordings define the type of signal that will be used by the neural prosthesis. There are two big design choices, fundamental design choices at this stage. First of all, we need to decide which type of sensor of technology we'll be using for recording neural activity. In other words, how are we capturing the brain signal? As we will see in a minute, there are different options, different type of sensor with some pros and cons. And second, we also need to decide which brain regions we want to monitor. Are we targeting areas involving articulatory execution, in semantics, in perception? As you know, as you will see in a minute, also there are a lot of research in this regarding this. So let me start first talking a little bit about recording approaches for neural data. So in this slide, I'm showing you the three main invasive techniques used in studies in this field, which are stereo EEG, electrocorticography or ECoG, and intracortical microelectrodes. I have organized them in terms of invasiveness. So why invasive? Because so far, the highest performing neural speech processes rely on invasive recordings on this type of sensor because they offer better spatial resolution, better signal quality than non-invasive methods. Having said that, I will come back to this non-invasive method, such as EEG or MEG, later on in this talk. Okay. So let me give you some more details about this technique. So in sEEG, which is this technique, and it's the one that we normally use in our studies. So they involve invasive implantation, like of electrodes, this side, inserted in the brain. And they are commonly used in clinical setting for epilepsy monitoring. As advantage, it gives us access to deeper structure in the brain. But as you can see, normally we have a very sparse representation coverage of the brain. So we only have a few. And normally, because those are epilepsy patients, the electrodes are normally placed on areas which are not typically involved in language production. So the second best method is electrocorticography, ECoG in short. And in ECoG, as you can see, place electrode grid over the exposed surface of the brain. So it required a craniotomy. It provides a strong, stable signal, and as we will see, has been widely used for speech decoding, especially over the motor cortex. And finally, what I consider is the state of the art, or the gold standard, are these intracortical microelectrodes. So as you can see, they are very small type of microchips with a lot of contacts, like normally 64, 128, or even 256, which penetrate in the cortex and can record activity from very small populations of the brain. So even at the level of detail of single neurons. So this gives us very fine-grained information, but the extent of limited coverage, because you can see they are very small, like 3 millimeters, very small, like 3 millimeters, and long-term stability. So these start to fail after a few months. I'll skip this slide. So once we have just discussed recording techniques, that immediately raises another question. Which brain region should we actually monitor if we want to capture linguistic information? So we know for a decade of neurolinguistic research that language and speech is not localized in a single brain area in the brain, but it involves multiple regions in the brain operating at different representation scale. So here I'm showing a classic atlas of the brain showing the main region related to language and speech. In this table, I'm organizing these regions according to if they are involved in more semantic or abstract meaning of the language, or more concrete, more motor commands. So we know from this research is that temporal regions over here are involved in more semantic, processing of more semantic, more abstract information. Frontal regions here contribute more type syntax processing, while the motor area here is responsible for articulatory planning and execution. So as a summary of all these key takeaway that I want you to take is that language and speech are distributed in space and time in the brain. So there is no a single brain language area or speech area in the brain. So there are different levels of representation like semantics, phonology, articulation that are handled partially by different parts of the brain. To reinforce this idea that language and speech is distributed in the brain, I'm showing here some diagram extracted by a very relevant influential study called the Semantic Atlas by Hood and colleagues from 2016. So in this study, what they did is they map fMRI recordings during natural storytelling from, I think they were using seven participants, to the brain. So they map the semantic information during this story listening from the participant to different part of the brain that activated the most during this semantic configuration. Okay, so a summary, as you can see here, you can see in this graph that different colors represent different semantic concepts like numeric, visual, violent, abstract, of different semantic meaning. So as a takeaway from this is that first of all, semantics is not started in a single location, but they are distributed across different regions of the brain. And sorry.
José Andrés, we cannot see your cursor. Sometimes it looks like you are pointing to some drawings or whatever.
Okay.
Just to know.
So, yeah. Okay. So, so the key takeaway is that language meaning is distributed across large part of the brain, and this was consistent across individual. So again, this study supports the idea that language, even at the level of meaning, is widely distributed rather than being localized into a single area of the brain. But now comes the interesting contrast, and is that when we look at the literature of neural speech processes and speech BCIs, even though we know that language processing is distributed across multiple regions in the brain, we see that most high-performing neural speech processes today almost exclusively focus on the motor and premotor cortex. You can see here that more in some of the studies, they focus only on recording this video. And why is that? So there are practical reasons and functional reasons. The main practical reason is because, as we will see, most of these studies use these microelectrode arrays, and because they are so small, they prefer to just record this area because you cannot cover, the coverage is limited. And also the motor area, as I mentioned before, is related with planning of articulated gestures. So actually controlling how our mouth and tongue move. So this is more closely related to the phonetic output, what we want to decode. And also the signal from this area are relatively strong and easy to model. So in practice, while language is distributed across semantic large region of the brain, current neural speech processing mainly decodes this articulatory layer. And this is an important perceptual gap between what we know from neuroscience and what currently BCIs are doing. Okay. So far, I have talked about applications, experimental paradigm, and recorded technologies and brain region. And now I'm arriving to the last part of this talk, what I really consider that is the core of this talk. So it's the decoding techniques that have been used for decoding speech, either as text or audio from this neural signal. Because ultimately, once we have neural signal recorded from a given region, everything depends on how we translate the signal into meaningful output. And doing a literature review, this is where the field has evolved the most over the last 10, 15 years. So in this section, I would like to focus on this evolution, how the problem has been framed, and how the modeling study has changed over time. So as its core, neural speech decoding is just a machine learning problem, and the goal is straightforward to state. We want to translate neural activity recorded during a speech task into linguistic units, either text or audio. And conceptually, you think about it, this is not very difficult, very different from a classical automatic speech recognition system. The main difference is that while in automatic speech recognition, we map acoustic signal to text, here we are mapping neural signal to text or speech. So this is how a standard pipeline in neural speech decoding looks like. So we start with the neural signal, and this signal undergoes some form of preprocessing, filtering, normalization. We'll see in a minutes. So the feature extracted and then fed into brain to speech model, which could take any form, like statistical model, neural network, whatever. And finally, we obtain an output that could be either text tokens or synthesized speech. So as you can see, the pipeline is familiar to anyone working on speech technology. So the main difference is that the front end here is the front end signal are neural rather than acoustic, and this make neural front end make more challenging than a standard speech front end, because neural signals are noisier and more variable across individual and much less standardized. And also, another problem is that the data sets used for training this model are higher, several order of magnitudes smaller than typical speech dataset. So before we move to, or we talk about the decoding model, I would like to spend some time about to look at what a typical neural signal pipeline looks like, because normally in practice we don't take raw neural signal and directly fed them to like a machine learning model. There is always some intermediate layer signal preprocessing. So this is how a common pipeline looks like. At the beginning, we have the raw signal, and then we apply some renoising, for instance, applying a notch filter to remove power band lines, referencing the signal property, etc. Then we apply some bandpass filtering to isolate frequency rates that are known to carry linguistic information. For instance, it has been shown in different research that the high gamma activity that goes between 70 to 150 hertz is strongly associated with speech production. This is in ECoG and sEEG in intracortical electrodes. Instead of frequency band, researchers often work with spike counts because we are working with spikes and local field potentials. After this filtering, the features that we extract are normally segmented to short temporal windows from 20 to 80 milliseconds, and then these features are normally across all channels. So moving on, now that we have seen how neural signals are processed and converted into features, we reach the core of the system, the decoding model. And this is where neural activity is translated into text or speech. And this is also where the field has really evolved the most over the last 10 to 15 years. So here I'm showing you a diagram with the evolution of these modeling techniques in the last 15 years. So you look at the trajectory, you notice that it almost perfectly mirrors the evolution of automatic speech recognition. So in the early approaches relied on linear regression or Kalman filter that were suitable for small path constrained tasks, but were not scalable. Then researchers, like in automatic speech recognition, started to adopt standard or classical ASR pipeline using HMN-GMN's model, phone level decoding, n-gram model for language modeling, so on. And then just like in automatic speech recognition, deep learning changes everything, and people start using recurrent neural transformer, end-to-end architecture, and so on. And what we see today is that more and more studies are moving towards end-to-end models, streaming architecture, and also there are some attempts to build a foundational model for neural signal. We will talk a little bit more at the end of this talk. So in summary, we see that the trajectory of this field mirrors what the evolution of automatic speech recognition. Again, the difference is that instead of using acoustic signal, we are using neural signal. So in the next few slides, I will illustrate this progression with a few landmark studies. So the first study I would like to talk to you is one of the early landmark studies in this field. It's the work by Genter and colleagues from 2009. So I'm including this study because it was one of the first demonstration of a real-time neuroprosthesis. So in this work, they implanted a participant with locking syndrome, so the participant could not actually move, with a single two-channel neurotrophic intracortical electrode in the motor cortex. Okay. They recorded neural activity from this area, and using a Kalman filter, they predicted two acoustic parameters, specifically the first two formats, F1 and F2 of speech. So rather than decoding words or phoneme, they decoded articulatory continuous acoustic control signal that were fed into CLAD type format synthesizer. For you who has worked on speech synthesis, you know that CLAD synthesizer is a classical speech synthesizer working with formats. And what is interesting about the study is that it operated in real time. So the latency was less than 15 milliseconds. Even though the only work in the vocabulary was only vowels, the system was able to provide a closed loop closed-loop speech in less than 20 milliseconds. So the main result of this system is that it works in real time, and also because they implanted this participant over a few months, 5 months, they show that the participant improved in vowel production with practice. So this again is one of the foundational study. So I will skip this video because we are running out of time. I can play for you later. So moving on, in 2015 we have also a very important study in this field by Christian Herf and colleagues. So this study here was one of the first attempt to apply classical automatic speech recognition algorithm to neural decoding. So in this study, the participants were epilepsy patients that were undergoing clinical monitoring, and they were implanted with ECoG, with electrocorticography sensor, and they asked the participant to produce between 5 to 10 minutes of a speech, so over speech, allowed. Okay. And this is a brain-to-text study, so they try to decode the text, to decode the speech from the neural activity. And for that, if you look at the picture, they apply a classical ASR pipeline using Gaussian mixture model or Gaussian. In this case, they were using just Gaussian model from modeling, HMN decoding, bigram L models. So essentially just a copy of a standard HMN GMM model at the time. So the results, as you can see, were not very amazing. They obtained like around 25 word rate in a vocabulary with 10 words, and around 50% phone error rate. So no amazing. But what makes this study historically significant is that they show that an ASR toolbox, originally developed for acoustic speech recognition, could be directly repurposed for neural speech decoding. And then 10 years later, in 2014 and 2024, we have a paradigm shift, and we have this study from CART and college that we see something different from the study before. So unlike the study from Christian and group, from Christian Head, to work with epilepsy patients that were monitoring during epilepsy, in this study was developed for a participant who really needed this kind of interfaces. So the participant was a participant with ALS, with sclerosis, who had not the ability to speak. So actually, this was part of the clinical trial, whose goal was to evaluate, to figure out if this neural speech prosthesis could work and could restore one person communication abilities. So this was not a lab experiment. This was a real attempt to restore communication in someone who has lost the speech disorder. So apart from this, we also can see that the architecture they use for decoding is more modern. So they use an array of intracortical electrode with 256 electrode. They use a recurrent neural network phone decoder, a transform-based language model. What is really surprising in this case is that they implanted the patient for with these electrodes for 8 months, and they have a huge data set of sentence. Regarding the results are also amazing. They got like 97.5% accuracy over 8 months, speed rate about 32 words per minute. So in here, I'm showing you a video of this system. So this is the patient using the interface. He's doing free speech. So I think they were talking about going to the movies. So you can see over here the implants. They are transmitting wireless speed and providing power to the implants. And the screen is just showing what the system, the neural interface is encoding. Apart from that, the system includes an eye tracker in here that the user can control to like click different buttons. Okay. So another similar study from last year is this by Warakar and colleagues from 26 from last year. This is similar study. It was also working with the patient with ALS. But this is an example of brain to audio approach. So rather than decoding text, they were proposing mapping directly neural activity from intracortical electrodes into speech features. So they were specifically using capsular features plus pitch, prosody, pitch and voicing using LPCnet-based vocoder. One of the key components here is that the whole system runs in real time under 10 millisecond latency, so enabling this user in the loop system. So it's best if I show you a video of how this system works. This is a system.
This is really very good.
So this is what it is called a copy tag. So the participant is being presented with a sentence, and he's trying to repeat the sentence using imagined speech.
Well,
so the system is able to synthesize the speech is being decoded and also recognized. This runs under 10 milliseconds.
I can see or and there. Ow. Oh. You. I can see
okay, so you can feel the difference. Okay, so as a summary of these studies we have just seen, in this slide, I'm highlight some of the key milestones in this field. So starting in 2009, we see that in Genter and college, we have a real-time vowel synthesis from single intracortical electrode. Then in 2015, with Christian Herd, we have continuous brain-to-text decoding. So continuous brain-to-text using a standard ESR pipeline. And then more recently, in the last two studies I've shown, we see large vocabulary system, a real-time voice to brain to voice system with prosody in real patients. So this is one of the key. Summary, we see that just in over a decade, neural speech interfaces has evolved from control lab demonstration to systems that start to resemble functional communication tools. And this progression, I think, reflects the advance both in the neural recordings, architectures, model architectures, and also this longitudinal strategy. So we are running out of time, but before moving to the conclusions, I would like to briefly show you some of our recent work in this field. So in this slide, I'm summarizing two of our recent studies that we presented last year at ECoG and InterSpeech. The first one, the neuroinset work that we presented at ECoG, we conducted a study with 10 epilepsy patients. So you can see here the fMRI of the 10 epilepsy patients with the stereo EEG electrode implanted, and you can see that how different are the placement of electrodes across all participants, because of course the placement was only guided by a clinical decision. So in this case, this was a brain to audio approach. So instead of decoding text, we directly reconstructed log MEL spectrogram for high gamma activity recorded during speech production using a model inspired by perception. So it was a pure neural to acoustic mapping. So in result, what we obtain is we evaluate the system, this reconstruction using objective metrics. So we essentially use the Pearson correlation between the predicted spectrogram and the spectrogram obtained from the original audio recordings from the patients. We got very high reconstruction accuracy ranging from 0.8 to 0.9 correlation. And in the second study that we presented at InterSpeech, we flipped the problem. So for each of these patients, we also use this dataset from each patient. And for each patient, we have a list of words recorded by the patient. So the text, the audio, and the neural activity recorded by the patient. I was telling that we flipped the problem. So instead of decoding speech from the brain, we ask, can embeddings from large speech and language model reconstruct neural activity? So what we did is we fed this word embedding to these FastText and GPT-2 models, and also the audio, the original audio spoken by the participant to a WebTube model. So and from this embedding, we try to reconstruct the neural activity during the production of this activity word. So here the direction was from embeddings to brain features. And what we found is that remarkably high reconstruction accuracy. So for the FastText and GPT-2 embeddings, correlations between the reconstructing neural activity and the ground truth ranged from around 0.8 to 0.9 correlation. So this, I think this suggests that this large self-supervised model encodes some representational structure that aligns with cortical high gamma dynamics. So in other words, these models are not just engineering tools, but they may approximate to some extent the way that language is processed in the brain. So this were some words doing speech reconstruction or neural reconstruction, but we are also delivering some data set to the community. So here I'm summarizing what EEG data set that we just released openly to the community, and it features EEG audio recordings for 15 Spanish participants, and it features open imaging speak and over speech with for different speech stimuli like syllables, real words in Spain, Spanish, and we use different stimuli like text, audio, pictures. So the code, the dataset is publicly available for anyone, and we hope that the community find it useful. Let me know if you have any feedback, suggestion, or maybe collaboration. So conclusions. What should we take away from all this talk? So first of all, we have seen that fluent neural speech decoding is no longer science fiction. It is technically feasible now. Part of this is is due to improvement in high resolution neural recordings combined with model deep learning architecture that makes this possible. Also, we have seen from the evolution of the coding architecture there, of the coding techniques that architecture matters. So the transition from linear model to deep sequence-based deep learning architecture have fundamentally changed the performance levels of in this field. So what about futures? Of course, there's still some open challenges that I'm discussing in this to be solved and discussing in this slide. First, one big challenge that needs to be addressed is data scale and foundational model. So neural dataset required for training all this model are still small and highly specific, subject specific. Despite recent effort to build foundational model for this in this style, like there was one recent attempt like Parista, there's still much to be done. Second, cross-subject user generalization. Most systems still require individual calibration for each subject. Maybe moving toward shared learning space, that may be a key step. Long-term stability and implant longevity for this implant. Also, we mentioned the 4 points about non-invasive decoding. There is still this question if whether non-invasive modalities such as EEG or MEG combined maybe with modern deep learning architecture and large training data set can narrow the gap with invasive technique. And finally, clinical validation, of course, of these devices. So I think if we can solve this challenge, maybe neural species interfaces could be called transformative in technology for people who have lost the ability to speak. That's all for my part. Thank you very much for your attention. I will be very happy to take any question.
Okay, thank you, José Andrés. It has been very, very interesting. We are almost out of time, but I think we can have some time for some questions, short questions, please, and short answers. Is there any question over there? Yes, Javier.
Hello, do you hear me?
Yes.
Yes.
Okay, but very interesting, the talk. I have a very short question. You mentioned that you use high gamma activity frequencies to decode from them. Has this been widely tested in ECoG or in these invasive techniques? Because in MEG, we found that lower frequencies also have some speech information, but I don't know if this is shared with your techniques.
Yeah, so normally we use high gamma, but there are also like lower bands like theta or something like that and they also carry information. Yeah.
Okay, thank you. Yeah, in our experience in MEG, our short experience, frequencies beta and lower has more information than higher frequencies, but of course the technology is different. So yeah, thank you.
And I also think that maybe for non-invasive like MEG or EEG, also high frequency bands are also more contaminated with muscle movement, so they are less robust than in invasive techniques. So invasive technique, when we work with data from epilepsy patients, they are not that affected by head movement or eye blinks or so on.
Yeah, probably, yeah.
Any other question? Yes, Sanai.
So, hello, do you hear me?
Yes.
So, my name is Sana, and I am a PhD student from Morocco, and I am working on decoding EEG signals and convert it into text. So, I'm not yet collected our own data, and actually I worked with open data sets. So while I'm working with the 2020 international data BCI competition data sets, I realized that each subject used different regions of the brain. And the results related to accuracy within subject demonstrate this difference between subjects. So my question is, there exists, is there a model that can be customized the pre-processing? So instead of working with the same pre-processing on the all subjects, we can customize the pre-processing based on each subject.
Do you mean by for feature extraction or like what do you mean?
For example, channel selection. Instead of working with the same channel selection for all the subjects, we can apply a customized pre-processing on each subject and extract which channels are most interesting for each subject.
I'm not aware of this kind of model. What I'm aware is that little by little people are trying to work on foundational models. So there was one recent paper, the barista paper I mentioned, that where they wanted to build a foundational model for sEEG, where as I have shown in the slide, the coverage across patients is different. For standard EEG, I think there are some attempts also to replicate some of the model like back-to-back, but for EEG. But I'm not aware of what you have mentioned.
Okay, so what if we can create this kind of models and it can help or no? Especially I'm a PhD student, so I am very stressed with time, and I need to deliver a final thesis. So I need a pathway to, if I worked on this problematic, can I?
I think maybe you can write me later. Maybe I can reply by email.
Okay. Okay, thank you. And my second question is, while should I focus on one subject and a large vocabulary, or a few vocab and a large number of subjects?
For EEG, what we have seen for standard non-invasive EEG is that EEG, the quality of the signal doesn't allow you to decode like large vocabulary. So what people have shown is that it's better for standard EEG to decode a vocabulary with few words and with a lot of repetitions. So you may maybe want to have a look to the data set we just released. We have like 6 words and 60 words, and these 60 words are from 6 semantic categories. So like part of the body, animals, and something like that. And we have like a huge number, like 300 or something like that trial for each participant.
Okay, thank you so much.
Okay. Thank you. I don't know if we have any other participants who wants to make a question. No? Okay, I think it's high time now, so we can close here. Once again, thank you very much, José Andrés. It has been very interesting. Thank you for coming and giving us this nice talk. See you next in next years in this series. Probably we will go on collaborating with you, and you will have probably more results to tell us. So thank you very much.
Thank you for the invitation. Okay, bye-bye.
Bye.